All right, so we're gonna look at the next question, okay? This time we had two equations, right? Two equations. We wanna transform this system of ODEs into an equivalent system of first order ODE. And notice that in this existing system, we have second order, right? Second order derivatives. We wanna transform them into a system of first order ODEs, like kind of similar to what we just did, okay? Any thoughts?
Would we set up like X1s and Y1s, or
yes, we need to have both X and Y's. Okay, good thoughts. So X double prime, so we should have a bunch of X's. There's Y double prime, so we should have a bunch of Y's. Okay, so let X1 to be X, X2 to be X prime, and that should be fine for X's. For Y1 to be Y, Y2 to be Y prime. Is that good so far?
Mm-hmm.
Then we would have X1 prime. Derivative of X1 is X prime, which is X2. And then X2 prime, which basically, okay, let's do here. So X2 prime, we understand that's X double prime, right?
Mm-hmm.
And based on this equation, number one, do we know what's X double prime?
Yeah.
It's 5X minus 4Y, right, from the first equation.
Would it be 5X or 5X1?
Yes, so we're going to replace these X by our new variable, X1, so 5X1 minus 4Y1, right? So we're going to put that in the system equation here. So 5X1 minus 4Y1. Is that good?
Mm-hmm.
Similarly, you guys please write down the equation about Y1 and the equation about Y2. Do you guys come up with these two additional ones?
Mm-hmm.
Y1 prime will just be Y sub 2. Y2 prime is Y double prime, right? So Y2 prime is Y double prime. So based on the equation number 2, that will give us negative 4x plus 5y, which is negative 4x1 plus 5y1. Good so far? Any questions?
Mm-hmm.
All right, notice that the reason that we're confirming, we're transforming is all of these systems that we constructed after the conversion, they are all first order ODEs, okay? The first order ordinary differential equations. And remember in chapter 1, we talked about a lot of first order differential equations, right? There are all kinds of methods for us to solve first order differential equations. So by converting all those higher order differential equations into first order systems, those methods we learned before could apply. Good so far, you guys?
Yeah.
Other folks?
Yes.
Okay,
Yeah,
great.
Yep.
Okay, can we move on to the new section?
Yeah.
All right, so we're gonna move on to the new section 5.2. It's also on the Maya courses. Did you guys get a chance to download it? I'm sorry, I just uploaded like 10 minutes ago-ish. But if you have a computer in front of you, you can open that in OneNote. Okay, OneNote, and then make notes in there. Or you can make notes right now or just follow what we do instruction in class, and later on you can look at the annotated notes I would upload on my courses. Okay. So this section is called the method of elimination. Okay, method of elimination. Have you heard of this name somewhere before? Method of elimination?
Sounds like system of equations.
Yes, that's where we have learned to solve system of equations, right? And the system of equation we know before is algebraic linear system. Let me see. So suppose we have algebraic linear system. For algebraic linear systems, they look like these. And of course, if you have taken linear algebra, you know there are like other more complicated systems, right? But they're all linear. So this is a very simple linear system of two variables and two unknowns. If you are given this equation, how would you like to solve this?
Just multiply the top equation by 4 and subtract them.
Okay, good. So you can do elimination method, right? What other method we can do?
Substitution.
Yeah, a substitution method. Okay. How about we try substitution method first, and then we're gonna go to the method of elimination. Okay. So let's try substitution method. The reason we're doing this is because one of the equation, for equation number 1, is relatively simple, right? We have x minus 2y equals 3. So that will give us x equals to 3 plus 2y. Let's call this equation 3. Yeah, we have equation 1 and 2, so this is equation 3. And I'm sure you guys know what to do next. Next step.
Plug it in.
Plug into equation number 2. We have 4 times 3 plus 2y plus 3y equals negative 10. Combine the like terms, distributing the 4, combine the like terms, so we have 8y plus 3y, that's 11y, plus 12 equals negative 10. That tells us 11y equals negative 22, y would be negative 2, right? And therefore, what's going to be x? 3 plus x will just be obtained from equation 3. 3 plus 2 times y, which is negative 1, right? So we have x, y as negative 1 and negative 2, respectively. Is this good? I think you guys, this should be pretty easy for you, right?
Yeah.
Okay, so similarly, let's apply the method of substitution, which is, I think a lot of you guys actually like substitution method a lot. So let's try the substitution method for the next system, okay, which is differential system of differential equations. So equation 1, equation 2. I'll give you guys a few minutes, okay, for substitution. I'm gonna mute myself. You guys can talk if you want to. Okay. Okay, have you guys finished this question? Can I ask which equation did you guys start with? How many of you started with equation 1?
I did.
Me too.
Okay. Actually, these two are pretty similar, right? Equation 1 and equation, they're pretty similar. Both of those has one variable, and the other two terms are about other two variables. I think coefficient-wise, equation 1 is simpler, so I'm going to do starting from equation 1. X prime equals x minus 2y. So can we solve for y?
Yeah, plug in into the second equation. What we have.
So y would be, if I move y here, so 2y would be x minus x prime, right? So y would be x minus x prime divided by 2. You guys have these? And next step, Milan, did you plug this into equation 2?
Yes.
Plug into equation 2, I have y prime. So x minus x prime. This is y prime equals 2x minus 3 times y. Right, get down to here. So that is 1/2 x prime minus 1/2 x double prime. I distribute the prime onto the top. On the top, you have 2x minus 3 over 2x, and then plus, so minus turns to plus 3 over 2x prime, which you can combine these two x terms. That will be 1/2 x plus 3 over 2 x prime. What's the next step, folks? Once you reach this step, what do you do?
Solve for x of t.
Yeah, solve for x of t. But first of all, let's see, we would like to arrange everything to one side, and right-hand side would be 0, right? So I'm going to keep the higher order derivative, which is negative x double prime over 2. And then first order derivative, which will be x prime over 2 minus 3 over 2x prime, so which is minus x prime. And also move this 1/2 x to the left-hand side, so minus 1/2 x equals 0, right? You can simplify this look if you don't like the negative as well as these divided by 2. So I'm going to multiply both sides. Both sides by negative 2. I'll get x double prime plus 2x prime plus x equals 0. Folks, do you have these?
Yep.
Okay, good. Halfway through, right? So let me see. Where's my pen? Pen. So this is homogeneous, right? Equation. We should again use the characteristic equation, which is r squared plus 2r plus 1 equals 0. This could be factored as r plus 1 squared equals 0, meaning there are 2 repeated real number roots, right? So 2 repeated real roots. Okay, do you have these?
Yeah.
Okay, so let's see if I have space here. Yep. All right, so then that tells us at least we can solve for x now. So x of t, based on these two repeated real roots, I had c1 e raised to negative t plus c2 t e raised to negative t. Right?
Yeah.
Okay, so that's x of t. Then similarly, I can have y of t, okay? Because y of t, according to what we did previously, y of t is x minus x prime over 2. So that is x subtract its derivative and then divide by 2. Okay. I'm going to save some time here in terms of the calculating. Do you want me to show you the steps for the subtraction? I think you guys should be able to handle this, right?
Yeah, that's fine.
Let's write down the solution. So eventually you can pull out e to the negative t, and then you have 1/2. On top you have 2c1 plus 2c1 plus 2c2 t, and then minus c2 e raised to the negative t, which you can write also c1 plus c2t minus c2 over 2 e raised to the negative t. But anyway, these two are going to be the solution to the system, right? Are these two problems fine with you guys?
Yeah.
I think the system is similar to one system that we talked about last time when we introduced the system of equations. So these two problems, basically we used substitution method, right? And we see substitution method basically is, first of all, you solve one variable in terms of the other one, and then use that relationship to solve the other variable. Okay. Substitution method. Now we're going to focus on elimination method in general for system of equation today. In general, elimination method, I think Haziel, right? Haziel, hello? Haziel? Haziel? Are you napping?
I guess you took a break.
Haziel, you're back?
They say that the microphone is not working in the chat.
Oh, okay, great. Thanks for the indication. So when we first brought up this question, Haziel was responding saying that we can use elimination method, right? So elimination method, if we revisit that simple system, elimination method will basically trying to eliminate one variable first, right? Now, in this case, you can either eliminate the x or you can eliminate y, but the x will be easier to eliminate because equation 1, coefficient of x is only 1. So I can do equation 1 multiplied by 4. That gets us 4x minus 8y equals to 12. And then along with the original equation 2, it's 4x plus 3y equals negative 10. This is the original equation 2. I'm going to name the equation multiplied by 4 as equation 3. So this would be the new system. What do we do next, folks? Subtract? Yeah, so you can do either 3 subtract 2 or 2 subtract 3, doesn't matter. Subtract, so the x will all be eliminated. And we only have negative 11y equals to positive 22, getting y equals to negative 2, right? And then you either use equation 1 or equation 2, you can get x. So x would be, this is a negative 1, right? So that's the elimination method. So the key for elimination method is you want to eliminate one variable first in the system, okay, in the system. So try to get rid of the x or y first of all, okay, in the system. The elimination this method can also be applied for a linear system, okay, linear system. But right before we actually apply for the linear system, let's try to recall this polynomial differential operator L, okay. Did we talk about L before, you guys?
We just mentioned it, but not.
Yeah,
in
we
detail.
do on Ly. Recall this? Ly equals 0. Ly equals f of t. When we're talking about homogeneous and non-homogeneous. Was that in chapter 2?
Yeah.
Right. So this L is a linear operator. Okay, linear operator. It has derivatives. This is an nth order derivative. This n minus 1th order derivative, and the degrees of differentiation decreases to the first order to basically there's no derivative. Okay. Here D, this D is the one we'll be using a lot in this section. D is used for differentiation. Okay. This would also be covered in calculus 1, right? We've seen D2, D3. That means it's the second order derivative or third order derivative. Let's first familiarize ourselves with this D notation. Suppose we have this differential equation, x double prime plus y double prime plus 13y prime minus 4x prime minus sine 4t equals 0. Oh, sorry, there's no 0 prime, just 0. Okay, 0. How do we use this? How do we rewrite this in terms of the D?
In terms of parting?
Yeah, so yeah, how do we rewrite this?
D squared x
D squared
dt
x.
squared.
Yep, we can just
Or-
write D squared x plus D
D-
squared
y
I, right? It's y double prime plus 13 y prime. So that's dy minus 4 x prime. That's dx minus, there's no differentiation. So just sine t equals 0. Is that good?
Yep.
Okay. And the good thing of using the D notation is once you introduce the D notation, it looks like algebraic equation. Because there's no prime you should be struggling with, and you see a bunch of D's. Is that good? With this in mind, let's rewrite the following system. Okay, the following system example 2. X prime equals x minus 2y, y prime equals 2x minus 3y. The one that we did previously. I asked you guys to do it, right? This question right here. Let us rewrite everything in terms of the D notation, which is differentiation notation. Okay. So x prime could be read as
Yeah.
dx equals x minus 2y. Second could be read as dy equals 2x minus 3y. Let's call this equation 3, this as equation 4. Okay, so we'll just be focusing on equation 3 and 4. For these two equations, I can move everything to the left-hand side. So we have some x term, and we have some y term, okay, which is a linear equation, right? What's the coefficient for the first x?
1.
I would have
2.
x would be moved to the left-hand side,
D
right?
minus 1.
So D minus
Correct. Algebraically, we have d minus 1x. And then plus how many y's?
Plus 2y.
-2. Oh, 2.
Yep, move it to the left. Now it changes to 2y. Same thing for the right for the equation 4. I'm going to move this 2x to the left and move this negative 3y to the left. So I should have negative 2x plus d plus 3y equals 0. Is that good?
Yeah.
Yeah, so next we're going to treat this. Let's call this system star. So we're going to treat system star as an algebraic system. Okay. So if you have such algebraic system, how do we solve the system by using elimination method?
I mean, you would have to multiply each one using the. Oh wait, no, never mind.
Yes, you can keep going, Eric. We're going to multiply each
But
equation by a
the
certain
opposite.
value, right? Which variable you guys want to like eliminate here?
Y.
Okay, we're going to try eliminate y. Okay, so eliminate y. So if we're trying to do eliminate y, we'll have to make the coefficient of y to be either the same or completely opposite, right? Is that the idea? Either
Yeah.
same coefficient or completely opposite coefficient. Let's call this
Oh, yeah, that's what you're gonna do.
5. Let's call this equation 6. Let's make them the same coefficient. So I'm gonna do equation 5 multiplied by d plus 3. And equation 6 multiplied by 2. Multiply. Is that all right?
Yeah.
So we have d minus 1 times d plus 3 of x plus 2 times d plus 3y equals 0 times d plus 3, which is still 0. Let's call this equation 7. Next, I have negative 2. So this equation 6, everything multiplied by 2 times 2x plus 2 times d plus 3y equals 0. Let's call this equation 8. Right? So then we should be able to see that the coefficient of y are exactly the same. We can eliminate y by equation 7 minus equation 8. You guys following me?
Yeah.
Yep.
Yeah.
Okay. Once you eliminate this, there's no y. Right hand side will be 0 minus 0, which is 0. Left hand side will be some x, right? The coefficient would be this part, which we can expand as d squared plus 2d minus 3, and subtract negative 4, which is plus 4. Right? So this is d squared plus 2d plus 1x equals 0. What does it tell us? What does d squared plus 2d plus 1x equals 0 mean?
X is 0.
Don't forget about the D. Okay, Milan, now you got to go back to the D, right?
Just distribute.
Yes,
Then-
let's do D
and then
squared
solve.
X plus 2dx plus X equals 0. What is this equivalent to?
That's the same as x squared plus 2x prime plus that. Well, we have
The X double prime, right? X double prime. Remember, D squared is second order derivative. So X double prime plus 2x prime. Remember the D for differentiation. And plus X equals 0. Okay, does this ring a bell?
Yeah.
Yeah, this is consistent to what we had previously. Like, let's see, like in here, right? And then the following steps are exactly the same. You do characteristic equations, solve for the two repeated roots, and find the general solution for x of t, and then use another equation to solve for y of t. Okay. Let's see. Okay, so then you have r squared plus 2r plus 1 equals 0. Continues, we get x of t will just be c1 e to the negative t plus c2 t e to the negative t. Continues and getting y of t equals to blah, 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 right? You guys following me?
Yep.
Yeah, that's fine.
So basically, we're just using the elimination method, okay, along with the notation of D. Yeah, just simply along with the notation of D to solve for one variable, first of all. Once we got these equations with the D notation, we can convert that to differential equation and solve for one of the variables. Okay. So I want to emphasize the use of the D notation here in our solution. Let's see. So what we did here is we introduced the D notation. Therefore, we have converted the system into a sort of like algebraic system. Okay. Once you have algebraic system, you can use the elimination method to solve for one variable. And then the other variable can be easily obtained. Okay. All right, the next item in the section is number of solutions for a linear system. We talk about this topic if you have taken linear algebra before, right? Linear algebra, the students who have taken linear algebra, do you guys remember number of system to a linear system?
Yeah.
A little bit.
Yeah, Chase, you were in linear algebra last semester. Eric,
Yeah,
Philip, right?
Taking me back.
Bridget. Number of solutions to a linear system, you can have 0, could be 1, could be 0, 1, or infinity, right? But here we're looking at a linear system of differential equation. So it depends on the linear system you are given. Let's first look at this example. D plus 2x plus D plus 2y equals e to the negative 3t, and D plus 3x plus D plus 3y equals e to the negative 2t. How many solutions are there for this system? I'll give you guys a minute to think about it. Well, did you notice something in these equations that catches your attention?
You would.
What? Linearly independent?
They have same coefficients.
Yeah, it has same coefficient. Can we factor out these coefficients?
Yeah.
Yeah, equation 1, you can factor out D plus 2, then you have x plus y equals e to the negative 3t, right? equation number 2, we have, you can factor out d plus 3. Then you have x plus y equals e to the negative 2t. Let's call this equation 4. Can we try to use our elimination method? Elimination method, the basic principle is make sure they have the same coefficient, right?
Mhm.
But now they don't have same coefficient. So let's do equation 3 multiplied by d plus 3 and equation 4 multiplied by d plus 2. Is that good?
Yeah.
Then we have the equation 3 turns into d plus 3 times d plus 2 x plus y equals to d plus 2 e raised to negative 3t. Wow, second
Dr. Wu.
equation. Yes, is that Haziel? Question?
Yeah, it is. Quick question. Could you divide 1 and 2? Or
Now
you'd lose coefficients, but you would have t.
yes, intuitively, you guys would have probably thinking about dividing by d plus 2, but the question is, we cannot divide by a differentiation. Okay.
Oh yeah.
If you do dividing, you would have e to the negative 3t divided by d plus 2, right? This doesn't make sense because we don't have a function divide by differentiation. So dividing is not allowed. We can only do multiplication, okay? Sorry, only do multiplication, not division.
Dr. Wu,
No.
quick question.
Yes.
It would be d plus 3 e to negative 3t, right?
Huh?
Or-
Oh, yeah, my bad. D plus 3. Yeah. Thank you for pointing that out, Eric. D plus 3. Good. Let's continue. For the equation 4, I'm going to multiply d plus 2 both sides. So I'm having d plus 3 times d plus 2 of x plus y equals to d plus 2 e to the negative 3t. Negative 2t, my bad. Negative 2t, right? Okay, so let's see what this turns out to be. So we have d squared plus 5d plus 6 of x plus y equals to d plus 3 e to the negative 3t. What is this? What's d plus 3 e to the negative 3t? Folks?
Wouldn't you have to just take the derivative of e to the negative 3t? And then,
Derivative of e to the negative 3t plus 3 e to the negative 3t, right? Which is, what's the derivative of e to the negative 3t?
negative 3 e to the
E
negative.
to the negative 3t plus 3 e to the negative 3t. We got 0, right? Okay. Second part, the second equation, this part turns to be d squared plus 5d plus 6 x plus y equals to d plus 2 e to the negative 2t. Okay, so similarly, that's derivative of e to the negative 2t plus 2 e to the negative 2t, which is negative 2 e to the negative 2t plus 2 e to the negative 2t equals 0. That good so far? Almost close to the end. Okay, so after doing this, we've got, let me rewrite those two. Right, the first part, and second part turns to be d squared plus 5d plus 6 x plus y equals 0. What do you see about these two?
They're the same function.
They're the same function, right? So basically, even though this is a system, okay, a system of two equations about two variables, but the second equation is kind of like redundant, right? Because the information you get from the second equation repeats the information you get from the first equation. Make sense?
Yep.
So only the equation number one works, right?
Yeah.
Okay, so there's only one equation about two unknowns. How many solutions we can get?
Infinitely. Right?
Yes, so we should have infinitely many solutions of x and y. Because theoretically, you should have two different equations about two unknowns. Right now, we only come up with one equation about these two unknowns. Therefore, there should be infinitely many solutions that can satisfy this condition. Okay. So this question, again, we use the D notation. And we use the elimination method by making those coefficients be the same, right? Matching the same coefficient and do subtraction. Okay. Oh yeah, over here we didn't do subtraction, but you can tell once we got to this step, if you do subtraction, you get 0 equals 0. Okay, infinitely many. I'll let you guys try the second system to see how many solutions are there. The
I
second
have a
system.
question.
Yes,
If
Donovan?
we were to multiply the d 2 5d and the x y, would we get a problem similar to one in 5.1?
5 point. Which problem?
We have to substitute like x1 and x2 like for x and x prime. If we multiply out the d's,
Uh-huh. Are you, oh, you're talking about here, right?
yeah.
Yes, so basically this one tell us, are you trying to ask if I try to solve this, then basically I can distribute the x to all of these d's, distribute the y to all of these d's, right?
Can you do that? Yeah. I mean,
Sure,
not can you right
absolutely.
now, but is that possible? You don't have to do it now, but like.
Yeah, I mean, you can continue doing that. However, it doesn't give us enough information to solve for x and y's.
Okay.
Yeah, because you need to have one more information. I mean, you have two unknowns, right?
Yep.
So theoretically, you need to have two pieces of information to get a unique solution of x and y.
Okay.
In this question, we only have one equation about these two unknowns, so we should have infinitely many solutions of such x and y's. Make
Okay.
sense? Okay, I'll let you guys try next question. This time we're only looking at the number of solutions, okay? We're not actually trying to get the x and y. We want to try to get the number of solutions, whether it's unique or maybe infinitely many.
When we finish,
Excuse me. Okay, tell me which variables you guys were trying to eliminate in this question.
I want
Eliminate X.
X?
Oh no, sorry. I mean, I don't see that they're not the same.
Yeah, they're
Okay.
not the same.
Could you distribute the coefficients and then get rid of x that way?
Well, you can get rid of the x, but still but even if you get rid of part of the x, you still have d squared left for x, right? So that's not completely eliminated. How can we completely eliminate x?
divide by the opposite or whatever the other equation has for x.
Multiply or?
I mean multiply.
Yes.
It'll be nice. So factor out nicely.
So I'm going to do equation 1 multiplied by d squared minus 1. And equation 2 multiplied by d squared plus 1. So I would have d squared minus 1 times d squared plus 1 of x plus d squared minus 1 times d squared plus 2 of y equals d squared minus 1 times 2e to the negative t. The second equation turns to be d squared minus 1 times d squared plus 1. So d squared plus 1x. And d squared plus 1 y equals to derivative of 0 will always be 0. So this is equation 3. That's equation 4. Okay, this is quite routine, right? You just multiply the other coefficient so that they would have exactly the same coefficient. Then we can eliminate the variable x. Okay. So next, we'll eliminate x. Again, the way we do it is we do 3. You can do subtraction between these two. 3 minus 4. Okay. So it should be this part of y minus this part of y. I'm going to FOIL the first coefficient of y and then the second coefficient of y. Okay. If you FOIL the first one, what do we have, guys? D to the fourth.
Minus d to the second.
Yeah, minus d to the second and then plus 2d squared, right? So that's plus d squared. And then minus 2.
Yeah.
Okay, this is the coefficient of the equation 3, and then we should subtract the coefficient of equation 4, which is d to the fourth plus d squared. Okay, these whole thing
Times y.
would be coefficient of y. Is that good? The right-hand side, we should be doing this part of e and minus 0, which is just this part of e, right? So the d squared of 2e to the negative t minus 2e to the negative t. Now, in the left-hand side, we see that d to the fourth could be canceled out with d to the fourth. D squared could be canceled out with d squared, leaving only negative 2y equals to d squared 2e to negative t. What is this part, guys?
It's just 0.
Is that 0?
Because when you take the double derivative, you get 2 negative signs.
Yes, you're going to take second order derivative, right? So what's the first order derivative, Haziel?
Negative 2
2e to the negative t, right? And then take another derivative. What do we have?
2e to the negative t.
Yeah, so 2e to the negative t. And then minus 2e to the negative t. This is what you're talking about here, being 0, right? Okay, so good. So y equals to 0. Once y equals 0, you can use either equation 1 or equation 2, right? Okay, now I'm going to use equation 2. I just plug y equals to 0 in. So that just gives us d squared minus 1x equals to 0. I know you guys know how to solve this now, right?
Yeah, you just distribute
Distribute the d squared and distribute the x. So that tells us d
extra
squared x minus x equals 0, which is,
r squared minus 1.
yeah, x double prime minus x equals 0. Therefore, r squared minus 1 equals 0. R minus 1, r plus 1 equals 0. R1 equals 1, R2 equals negative 1. So, okay, this x of t should be c1 e to the t plus c2 e to the negative t, right?
Yeah.
Okay,
Yep.
so
Yeah.
that is the solution of the x. Here's the solution of y. Eventually, our solution will be c1 e to the t plus c2 e to the negative t, and y would be 0. So sort of we have a unique solution, right, based on the x and y's. Okay. Any question about this problem? Folks, any question?
No, I don't think so.
No, not really.
No? No question at all?
Yeah. Figure out.
Okay.
For the
Philip and Chase.
Dr. Wu, I have a question.
No.
I'm good.
Donovan? Yes.
So you said we're not allowed to divide. Are we only allowed to multiply? So we can't.
Yeah, because of the
We
d.
can't add, yeah, we can't add these.
You can't divide by d operator. Okay, d operator can only be multiplied.
Couldn't. Okay, yeah, okay, that makes sense. What about no? We couldn't do logs. We couldn't do like take the log of both sides with the d side,
Take logs? Oh.
like using logarithmic differentiation.
You can do derivative of the logs, right? That's
Yeah.
very good thinking. You can do derivative of logs, but can we do logs of derivative?
No.
No, not really, right? It's a very interesting idea. Okay. But in general, if you just treat it as algebraically, we don't use that logs that much here, Donovan.
Is it possible that we would end up with a d as an exponent?
D as an exponent? Oh, you mean? Oh no. Okay. D here is operator. So let me see. Let us recall the D notation. Okay. D notation. Where is our D notation? Somewhere here. Yes. Let me highlight this piece. When we use the D notation, okay, you're only using D raised to a certain power. See that?
Yes.
So D will always be the base. You see that?
Okay.
And this D raised to a certain power, even though it's written like this, but it actually means the n minus 1th order derivative. Okay.
Yep.
Yep. Okay. I hope this would be able to clarify your confusion. All right, so guys, next we want to look at the application of a linear system. Okay. Remember last time when we were introducing a linear system, we started with mass and spring problem. Okay. So we're going to look at a mechanical system of 2 mass and 3 springs. So let's start to sketching our graphs. Suppose you have the wall here in the left and the right, and to the on the ground. And we have 2 mass, mass 1, mass 2, M1, M2. There's 1 spring attached to the wall, another spring attached to the wall, and 1 spring attached to attaching these two masses. Spring constant of first mass is K1. Spring constant of mass 2 will be K2. Spring constant of the third mass is K3. Okay.
Before, did we use K3 as like F of T or is it?
Before, oh yeah, before we don't have this wall. There's no such wall. And there's an external force pulling M2. Yes, you are right, Eric. So this is a little bit changed from what we have seen last time, right? There's no external force. In this case, we only have 3 springs attaching to these two masses. Okay.
No, I haven't.
I have a question though.
Yes, question?
How do the system move or anything happens without the external force?
Well, you can give them some like initial initial velocity.
Ah, okay.
Yeah, initial velocity, like what we had before. Remember harmonic motion, right? There's no external force, but once it's given by certain initial velocity, it starts to move. Okay. Now let's suppose this M1, M2, these two masses are moving towards the right. And let's assume the displacement. Okay, so let the displacement of M1 be x of t, and let the displacement of M2 be y sub t. So this is consistent to what we did last time. So M1 is having displacement x of t, M2 is having displacement y sub t. From their equilibrium position. When it's called equilibrium position, it means this is the position when it's not moving at all, right? We're gonna construct 2 equations describing x and y. Okay, one equation about x, one equation about y. So let's first look at mass M1. How many forces attaching is on mass M1?
2.
2? Yeah. Okay. Should be some force from the spring K2, right? And some force coming from the spring K1. Is that clear?
Mm-hmm.
Yeah.
Okay. Now, for the force coming from the second spring, okay, it should be similar to what we discussed last time. It should be K2 spring constant times how much this K2 spring has been stretched or compressed, right? So Y2 has been moved to the right for the Y, so M2 has been moved to the right for the Y. At the same time, M1 has been moved to the right for X. So what is the total displacement for spring constant, spring number 2?
To y of t minus x of t.
Yeah, so it's Y minus X, right? Y minus X. And for the spring constant K1, it's the same case scenario as we have last time. So it'd be constant K1 times how much the spring K1 has been stretched, so it would just be X. Okay, so only these 2 forces on M1. Therefore, we should have total force, which is MA equals to K2 times y minus x, the force to the right, and subtract K1 x, which you can also write this as mx double prime equals to, let me put x together and put y together. Okay, so if I put x together, I'm having negative K2 minus K1, and the coefficient of y will be K2. Is that good for the mass M1?
Yeah.
Okay. Let's look at mass M2. Mass M2 is also moving towards right? So again, it's under two forces. The first force will be, let's see, from this spring, which would be, because it has moved to the right, so this spring will be compressed. You guys see that?
Mhm.
Well, let me move it to, so M2 would move to here, right? This is the wall. So the third spring will be compressed, therefore it should have a force onto the M2 pointing to the left. This force will be K3, okay, which is spring constant, and times how much it has been compressed. How much it has been compressed, folks?
Why?
Y. Good. And the other force will be coming from the second spring, right? The second spring. So the second spring has, let me use another color just to show you here. In terms of the second spring, it has certain force on M1, it has certain force on M2. They should be the same force in terms of magnitude, it's just a different direction. So it is pulling M1 to the right, therefore it should be having another force that's enforced on M2 to the left of the same size, K2 y minus x, for the same spring.
So
Make
Dr.
sense?
Wu,
Mhm.
if it's on the up, or I guess the negative version of the first force, would you write it as K2 x minus y?
Which one?
Two?
What do you mean by K2 x minus y?
So so you said that they're, oh wait, no, never mind.
in
makes
this
sense now,
case,
sorry.
both M1 M2 are moving towards right. Their displacement is to the right because
Yeah.
right is the positive part, right?
Mm-hmm.
Okay. So we talked about this last time. We said this K2 spring, okay, it has moved partly to the right for y's, and then the mass M1 also moved to the right for x. Therefore, the total, or the so-called net displacement for the spring number 2 would be y minus x. Make sense to you?
Yeah, it does.
Okay, great. Okay, so we've seen the total force on M2, right? On mass M2, guys, so let's write down the equation which is related to it, and then we'll be finished today. Okay. So we should have M2, oh, sorry, I forgot about M1 here, M1. M2, it's displacement, which is acceleration. M2, it's A equals to total force, right? F equals MA. So M2 y double prime equals to the total force. We only have two forces, okay? They're both pointing to the left. So they should have both negative signs. So negative K3y and minus K2y minus x. All right, so the system of equation about x and y could just be composed by using these two. Okay, let's finish here. So M1 x double prime would be negative K1 plus K2x plus K2y. That's first equation. Second equation is M2y double prime equals negative K3y minus K2 times y minus x. That's equation 2. Good?
Mm-hmm.
Let's
have a
stop at
question.
here, and next time we'll continue by looking at a specific situations when you are given with the spring constants.
I have a question.
Yes. Yes, Donovan.
Why is in the second equation why is it negative K2? Is it because the two forces are like opposing each other?
Oh, the second one? Okay,
Yeah.
hold on. Let me see. Where's my key? Where's my... All right. The reason is it comes from the same spring. Okay, first of all, it comes from the same spring of the spring number 2, right? So it should have the same force pointing to each other, you know? If it's on M1, it's K2y minus X, then on M2, it should be the same force, but opposite direction. And it's negative, okay? Are you asking why it's negative?
Yes.
Yeah, it's negative simply because, let me see, where's my pointer, guys? It's negative simply because both of these two forces, you see K3y and a K2y minus X, is pointing to the left. And when we say to the left, it is against the positive, it is against the positive direction. Therefore, you should put negative in front of those. Make sense here?
Yeah.
Okay, great. Okay, so folks, I'm going to post a new homework assignment on my courses. Also, I have created a link for you guys to post your assignment from last week. So feel free to submit your assignment there. Okay?
Dr. Wu,
Yes.
questions.
Yes, Martin.
First one is, about the next test.
Yes.
Will we have it next week as planned, or will we have it later?
Okay, first of all, it will be take home, right? Because there's no way I can do this thing in class. Is that a good news or bad news?
Good news.
Good news.
When are we originally scheduled for that?
Wednesday,
Did we
Friday.
schedule originally April the 1st?
I think so.
I will let you know on Wednesday. How's that?
Sounds good.
Okay, on this Wednesday. Okay.
The second question is,
Yes.
is there a chance to go over number 10 from the last test?
Number 10. Okay, we'll do that next time. Number 10.
And
Okay. We
last,
can do that, absolutely.
from chapter 4.5,
Mm-hmm.
there were parts in the exercise where you had to draw the graph. Is
Mhm.
there a chance that we could go over how to draw those graphs?
Draw graphs, like which graphs? Is it like solution curves?
In chapter 4.5, like in exercise 2, 3, or 5.
4.5. You're talking about
Yeah,
section
I agree with
4.5?
Martin. Yeah, stepwise functions.
Section.
Especially number 3.
Yeah.
Oh, which one? Number.
3. That one was the hardest one.
You talking about section 4.5, number 3?
Yes.
Oh, sketch the graph of f. Okay. If it's harder for you to sketch it by hand, then I mean, like,
Do
we'll
we
talk
need to
about that
convert?
in the beginning of next class. How's that?
Perfect.
Perfect.
Is that 4.5 number 3?
Yes.
Okay, great. Okay, we'll talk about that next time.
Okay.
Thank you.
I'll see you guys next time on Wednesday.
Thank you.
Thank you, Dr. Wu.
Thank you, guys. Mm-hmm.
Bye.
Bye.